Welcome, everyone. Ready to dive deep into isolated neutron stars.
Definitely always up for exploring these fascinating objects.
Today's deep dive is all about isolated neutron stars, using the paper The Zoo of Isolated Neutron Stars.
Sounds great. I think your listeners will really appreciate the depth we can go into with that source.
I think so too. As you know, isolated neutron stars are really unique,
Yeah.
governed only by their own internal mechanisms.
Exactly. Their behavior is so intriguing, and this paper, The Zoo of Isolated Neutron Stars, is such a perfect title.
Right. We are going to encounter a diverse array of neutron stars, each with its own unique quirks. We're going to talk about some really interesting questions too, like can a neutron star's magnetic field be too strong? What causes the different emission patterns in pulsars?
And could some neutron stars actually be masquerading as something else entirely?
Exactly. These are the questions that have been puzzling astrophysicists for years, and the answers are constantly changing as we get better telescopes and make new discoveries.
It's a really dynamic field, and I think it's important, like you said, to start with a really strong foundation.
Absolutely. So let's take it back to 1934 when Walter Bate and Fritz Zwicky first proposed the existence of neutron stars. Can you tell us about that?
Well, they understood that after massive stars run out of fuel, they undergo this catastrophic gravitational collapse. And they theorized that what would be left behind is this incredibly dense object made mostly of neutrons.
A neutron star.
A neutron star, exactly.
Then in 1967, Jocelyn Bell Burnell discovered pulsars, providing the first observational evidence for neutron stars.
Such a groundbreaking discovery, though at first they were quite a mystery.
Yes, the precision of their pulses led some to even speculate that they could be signals from aliens.
Right, but then they observed that the Crab pulsar was spinning down, meaning it was gradually slowing down.
So the energy lost as the pulsar spins down is what powers those emissions.
Exactly.
Now, we should be clear that we're focusing on isolated neutron stars today,
Yeah.
those that don't have a companion star.
Right, so we can really understand their intrinsic properties, without any influence from a binary partner.
So to navigate this diverse population of isolated neutron stars, we'll use the PO diagram. Can you explain that to our listeners?
Sure, so the P diagram is basically like a map. It charts the spin period of the neutron star, which is denoted by P, against its spin down rate, which is
So each point on the diagram is a specific neutron star,
Right.
and we can categorize different types of neutron stars based on where they fall in the diagram.
Exactly. Not only that, but we can also estimate their magnetic field strengths and their ages.
That's so cool. So let's move on to our first category, the rotation-powered pulsars, or RPPs.
RPPs are the most common type of pulsar, and like the name suggests, their emission energy comes from their rotation.
And there are a ton of them out there. Over 3,500 have been identified.
That's right. And they are spread out all over the P diagram, which reflects their really diverse range of spin periods and spin down rates.
So one type of RPP is the millisecond pulsar, or MSP. These pulsars are rotating incredibly fast, like their periods are measured in milliseconds.
That's right. It's because of something called accretion.
What is accretion?
So these pulsars were once in a binary system, and they siphon off material from their companion star. And this infalling matter actually spins up the pulsar.
Wow, it's like a stellar example of angular momentum transfer, right?
Yes.
So now we have radio pulsars, the most prevalent type of RPP. They emit radiation primarily in the radio part of the electromagnetic spectrum.
The radio emission is generated when charged particles are accelerated in their strong magnetic fields.
Okay.
So these particles move along the curved magnetic field lines and emit what's known as curvature radiation, and those make up the beams that we see as pulses.
Interesting. It's amazing how those magnetic fields create those beams. And I think it is fascinating that within the category of radio pulsars, there are some subtypes. Can you tell us about some of those?
Sure. One is called a rotating radio transient, or RRT. They have these sporadic radio bursts, not the regular periodic pulses that most pulsars have.
It's almost like they have a switch that turns their radio emission on and off.
Right, and then we have pulsars that exhibit nulling, where their radio emission just stops entirely.
So strange.
And it can last for periods from seconds to even days, and we don't really know exactly why they do this. The exact mechanism for nulling is still an open question.
And then we have pulsars that emit giant pulses, right? These super powerful bursts.
Yes, thousands of times brighter than regular pulses.
Wow. So are giant pulses showing us something about the extreme conditions inside the pulsar?
Exactly. It's where particles are accelerated to extremely high energies.
And then we have some recent discoveries like PSR J0250 plus 5044, PSR J0901 40046, Gleam X J162759.5, Pound 5235004.3, and GPM J183910.
Right.
These are challenging the concept of the death line.
Yes, this is a theoretical boundary on the P diagram where pulsars were thought to stop emitting radio waves, but these newly discovered pulsars are changing our understanding of that.
They have really long periods and still emit radio waves.
Yes, suggesting that the death line is not as absolute as we once thought.
I mean, it's like every new discovery is changing what we know about neutron stars. And it's not only radio waves that RPPs emit, right? They also emit in X-rays and gamma rays.
Right, and those come from different regions within the pulsar.
Also, can you break that down for us?
Sure. So the softer energy X-rays, the thermal X-rays, come from the hot surface of the neutron star itself, especially the polar caps. Those get heated by all the infalling particles.
Ah, okay. And what about the higher energy stuff?
The higher energy X-rays and gamma rays, the non-thermal emissions, those come from the pulsar's magnetosphere. Things like synchrotron radiation, where charged particles spiral along the magnetic field lines.
So cool. And then there's Fermi. The Fermi Gamma Ray Space Telescope has been instrumental in understanding gamma ray pulsars.
Absolutely. And then you have the pulsars that emit in the TeV range, like the Crab and Vela pulsars. Those are pushing the boundaries of how much energy particles can be accelerated to.
It really is amazing. And we can't forget about optical pulsars, even though they are faint and rare.
They give us some very important insights into emission mechanisms. The Crab pulsar, which was one of the first pulsars discovered, actually had polarized light, which supports the theory of synchrotron radiation.
Right, and then we have the connection between giant radio pulses and brightening in the optical bands.
Which suggests that maybe the emission zones overlap.
Amazing. Okay, I think it's time to move on to the magnetars.
Yes, I'm excited to talk about them.
Me too. They are some of the most fascinating objects out there.
Absolutely. So magnetars, as we understand them now, bring together what we used to think were two separate classes: anomalous X-ray pulsars, or AXPs, and soft gamma ray repeaters, or SGRs.
So they were once thought to be different, but now we think they are actually the same thing.
Exactly. They both have properties that suggest they are neutron stars with incredibly strong magnetic fields, like 10 euros to 10 years.
Wow, that is millions of times stronger than anything we can make in a lab.
It is, and these magnetic fields are what make magnetars so unique, and they drive all sorts of interesting behavior. They actually occupy a special region on the P diagram, slow rotation periods, several seconds, and their spin-down rates suggest they are relatively young.
So even though they rotate slowly, they are still very active.
Yeah.
You mentioned their magnetic fields drive a lot of interesting behavior, like their persistent X-ray emission.
Right, and that emission has both thermal and non-thermal components. The thermal part comes from the surface of the neutron star, heated to millions of degrees by the decaying magnetic field, also by the charged particles that are accelerated in the magnetosphere.
Okay, I see. And the non-thermal component.
That comes from the magnetosphere itself. Things like synchrotron radiation, where charged particles are accelerated to relativistic speeds and emit high-energy photons.
So the magnetosphere is like a giant particle accelerator powered by the magnetic field. Amazing. And I know that X-ray polarimetry is really helpful for studying magnetars.
Yes, it is. By measuring the polarization of the X-rays, we can learn a lot about their magnetic fields, things like the strength and geometry and the emission mechanisms. We've seen that the X-ray emission from magnetars is really highly polarized, sometimes even over 80%.
That's really high. What does that tell us?
It supports what's called the resonant Compton scattering model. This is a key mechanism for the hard X-ray component. So low-energy photons, probably from the surface of the neutron star, get upscattered to higher energies when they interact with the electrons in the magnetar's twisted magnetic field lines.
So the magnetic field isn't just accelerating particles, it's also increasing the energy of the photons. What about magnetars at other wavelengths, like optical and infrared?
They are tougher to observe because they are much fainter and there's a lot more dust in the way. We have identified some optical and infrared counterparts, but only for a small fraction of the known magnetars.
And what do those tell us?
Well, it seems like the optical and infrared emissions are non-thermal and coming from the magnetosphere. Curvature radiation, probably from electrons moving along the curved magnetic field lines, is thought to be a major contributor.
So even at those wavelengths, the magnetic field is still having a big impact.
Yeah.
Now let's talk about what really sets magnetars apart. They're transient events.
Yes, they are famous for their unpredictable and powerful bursts, and they can range from short bursts that last milliseconds to giant flares that release an incredible amount of energy in just a fraction of a second.
That's really amazing. Let's start with the giant flares.
Okay, so giant flares are super rare. We've only ever recorded three of them from three different magnetars. SGR 052666 in 1979, SGR 1900 plus 14 in 1998, and SGR 180620 in 2004.
And those were really powerful events, right?
Yes, huge bursts of gamma rays. The 2004 giant flare from SGR 180620 was actually so bright that it saturated instruments on a lot of spacecraft. It even caused measurable disturbances in Earth's ionosphere.
Wow. So what could cause these flares?
We don't know for sure, but the leading theory is that the magnetar's magnetic field suddenly reconfigures itself, maybe due to a buildup of magnetic stress in the crust or a change in the internal magnetic field structure.
Interesting. And I have heard that some people think that giant flares could be the source of short gamma ray bursts, SGRBs.
That's right. The energies involved are similar, and we do see some SGRB candidates that look like giant flares, like GRB 051103 and GRB 230115A.
So magnetars could be creating some of the brightest events in the universe. Let's move on to the short bursts now.
Okay, short bursts are much shorter than giant flares, obviously, and they happen much more often. Sometimes they occur randomly, and sometimes in clusters called burst forests.
That's a great name, burst forests. Do we know what causes them?
Probably smaller magnetic field reconnections in the magnetar's crust or magnetosphere.
Okay, and there are some magnetars that produce a lot of bursts, right?
Yes, like SGR 1935 plus 2154, it's produced tons of bursts.
And wasn't that the magnetar that provided a link to fast radio bursts, FRBs?
Right. Back in 2020, SGR 1935 plus 2154 emitted a radio burst that looked a lot like an FRB. It was the first time that we saw that kind of signal come from inside our galaxy.
So it made the connection between magnetars and at least some FRBs.
Exactly. It's a really good example of how diverse magnetars can be and how they can create some of the most interesting and puzzling events in the universe.
It really is amazing. And these bursts aren't just isolated events, right? They are often followed by longer periods of activity called outbursts.
You're right. During an outburst, the X-ray luminosity of a magnetar can increase by orders of magnitude, sometimes for weeks or months, even years before it goes back down to its normal level.
So what's happening during an outburst?
We think it's the release of magnetic energy that has been stored within the magnetar. So when the magnetic field reconfigures through things like crustal cracking or magnetic reconnection, that energy gets released, heats up the crust, and increases the X-ray emission.
So are there other things that change during an outburst besides the brightness?
Oh yeah, lots of things. The pulse profile can change, which suggests the geometry of the emission regions is changing. And then you have things like glitches and anti-glitches.
Glitches and
A
anti-glitches.
glitch is a sudden increase in the magnetar's rotational speed, and an anti-glitch is a sudden decrease. We think they are caused by interactions between the superfluid interior of the neutron star and its crust.
So outbursts really do give us a glimpse into the interior of a magnetar, how the magnetic field and the rotation are working together. I think it's interesting that some magnetars emit radio waves during outbursts.
They do, and sometimes they continue even after the X-ray emissions go back down. And the radio emissions tend to be different from typical radio pulsars. They're more variable and have a flatter spectrum.
Interesting.
One good example is XTE J1810197. It had a radio revival after its 2018 outburst. It showed narrow subpulses, changes in polarization, and even evidence of precession, which means its rotational axis was wobbling.
So magnetars are breaking down our categories of neutron stars. We used to think things were clear-cut, but then we have these low-field magnetars, the ones that act like magnetars but have weak magnetic fields.
Right, like SGR 0418 plus 5729, Swift J 1822.3, Sex 1 or 6, and 3XMM JWay 852 plus 0033. They challenge our definition of what a magnetar is. The external dipole field, the one we can measure easily, doesn't seem to tell the whole story.
So is there something else going on with their magnetic fields?
There might be. A lot of people think that these low-field magnetars have really strong toroidal magnetic fields inside, wrapped around the neutron star's core. Those could be much stronger than the external field.
So they are hiding their true magnetic strength. Is there any evidence for that?
There is. We see spectral absorption features in some low-field magnetars, and we think those come from proton-cyclotron resonance. That only happens in incredibly strong magnetic fields.
Okay, that makes sense. But then we have the opposite problem, pulsars that act like magnetars.
Yes, that's another cool twist. Some pulsars, like PSRJ 184600258 and PSRJ 11196127, they have magnetic fields that are typical for high-B pulsars, but they've had these magnetar-like outbursts, bursts and increased X-ray emission.
It's making things confusing, blurring the lines between the categories. So are we ready to move on to the X-ray dim isolated neutron stars, the Magnificent Seven?
Yes, let's talk about them. The Magnificent Seven are a group of 7 nearby neutron stars, all discovered in the 1990s by the Rosat X-ray satellite. They are kind of an odd bunch, really unique in the neutron star world.
In what way are they unique?
Well, they have remarkably low X-ray luminosities. That's why they're called X-ray dim.
Ah, okay.
And they haven't been detected in any radio surveys, so they must emit differently from normal radio pulsars.
So they're kind of stealthy.
You could say that. So we think that their faint X-ray emissions come from thermal emissions.
So the radiation is coming from the hot surface of the neutron star.
Right, which makes them perfect for studying neutron star atmospheres and learning about matter at extreme densities.
So we can look at their X-ray spectra and learn about the interior of the neutron star. What have we learned so far?
Their spectra are really well described by blackbody models, which means they radiate almost perfectly like thermal emitters. They're incredibly hot, between 50 and 100 electron volts, but their emitting areas are quite small.
Wow, that's so hot. But if they are so hot, why are their X-ray emissions so faint?
It's because the areas that are emitting the X-rays are so small. It's not like pulsars and magnetars that have big extended emission regions from their magnetospheres.
So it's a balance. The high temperatures but the small emitting areas lead to an overall faint X-ray glow. And they are rotating really slowly too, right? And they have weak magnetic fields.
That's right, which tells us they are pretty old.
So even though they are quiet, they still have some interesting features, like the absorption features we see in their spectra. What are those?
They're these dips in the X-ray spectrum, and we see them in 5 out of the 7 Magnificent Seven. We aren't exactly sure what causes them, but we have some ideas. Proton cyclotron resonance absorption is one possibility.
How does that work?
So protons that are trapped in the magnetic field near the surface of the neutron star, they can absorb X-ray photons at very specific energies. Those energies are determined by the strength of the magnetic field.
Oh, so by studying these absorption features, we could map the magnetic field strength.
Exactly. And the fact that these features change with the neutron star's rotation tells us that the magnetic field strength must vary across the surface.
That's really neat. Are there any other explanations?
There are. Some people think they come from atomic transitions in a thin atmosphere around the neutron star. The atoms absorb X-rays at specific energies, and those energies get modified by the strong magnetic fields.
Ah, okay.
And then another possibility is that they aren't intrinsic to the neutron star at all. They are just artifacts from variations in the temperature across the surface.
So like hot spots and cooler spots.
Yes.
We have a lot to learn about these features. Now, 2 of the Magnificent Seven, RxJ and 556.53754, and RxJ 0404050, they also have a weak non-thermal component in their X-ray emissions.
Yes, which is interesting because we think of the Magnificent Seven as being quiet with weak magnetic fields. But this non-thermal component suggests there might be some magnetospheric activity going on.
So maybe they are more dynamic than we thought.
Hmm.
And then there's the whole thing with the optical excess. What is that?
The optical excess is that all 7 of the Magnificent Seven are brighter in optical and ultraviolet light than we would expect given their X-ray emissions. So something else must be going on, another emission mechanism.
So it can't just be the thermal radiation from their surfaces.
Right.
Do we have any ideas about what this other mechanism could be?
Well, maybe the optical and X-ray emissions are coming from different places. Or maybe something in the magnetosphere, like charged particles interacting with the magnetic field, is boosting the optical emission. Or maybe they just have weird atmospheres that mess with how they emit at different wavelengths.
So many possibilities, but so few answers.
That's what makes this field so fascinating. And we are discovering more of these X-ray dim neutron stars with new instruments like Rosetta. So we'll get more data, and maybe some of these mysteries will be solved.
That's great. Okay, I think we have time for one more group of isolated neutron stars, the Central Compact Objects, or CCOs. They are found in supernova remnants, right?
Yes, right at the centers of young supernova remnants, which would suggest they are young neutron stars themselves.
So they should be active, but they aren't, right?
That's the thing. They are really quiet. They emit in soft X-rays, but we haven't seen them in radio or other wavelengths. They are totally different from pulsars and magnetars.
It's like they are hiding. So what can we learn from their X-ray emissions?
They are mainly thermal, and we often use a two blackbody model to describe their spectra. It looks like the emissions are coming from small hot spots on their surfaces.
If they are young, they should be spinning fast, and they should have strong magnetic fields, right?
You would think so, but only 3 CCOs have ever been seen to pulsate, and those that do have very slow rotations and weak magnetic fields. We call them anti-magnetars.
Anti-magnetars.
Yeah.
That's crazy. How is that possible?
One idea is that when they are born, they have normal magnetic fields, but after the supernova, material falls back onto the neutron star and buries the magnetic field.
So the magnetic field gets covered up, which explains why they are so quiet, but then why don't they have strong surface temperature gradients?
That's what we think. The buried magnetic field prevents the formation of extended magnetospheres.
Okay, so it's masked, but wouldn't it eventually reemerge?
We think it might. As the fallback material settles, the magnetic field could come back to the surface, and we might see it start to act more like a pulsar or magnetar.
So these could be late bloomers, so to speak.
Exactly, and there's some evidence for this. 1E1277.45209, a CCO, has had glitches, which could mean it has a hidden magnetic field. And the CCO in the Cassiopeia, a supernova remnant, seems to be cooling down, which could also be a sign that its magnetic field is coming back.
It'd be so cool to see that. But then we have 1E1613485055, which doesn't fit in at all.
Oh yeah, it's a real mystery. Its X-ray flux changes dramatically. It has a 6.67-hour period, which is weird. And then in 2016, it had a magnetar-like outburst.
What could that be?
There are a lot of theories. A neutron star interacting with a disk, a magnetar in disguise. We just don't know.
It really shows how much we still have to learn about neutron stars. This deep dive has been amazing. I have learned so much.
Me too. There's just so much diversity out there. Pulsars, magnetars, CCOs, each one with its own unique properties.
And they're all neutron stars. They're all born from the deaths of massive stars.
Exactly. And with all these new telescopes coming online soon, like the Square Kilometer Array and the Einstein Probe and Athena and the Cherenkov Telescope Array, we are going to be able to study neutron stars in ways we never could before. Who knows what we will find?
I can't wait. Thanks for joining us on this deep dive. I hope everyone listening learned a lot too.
It was my pleasure. Thanks for having me.